Welcome to class. Today we're talking about the final section of Chapter 3. Remember, Chapter 3 was our functions chapter, and today we're going to sort of hopefully tie a lot of the sections back together with the notion of an inverse function. So this is probably one of the most important topics in the entire chapter, both from an application perspective, so actually using this stuff, and also from the perspective of students going on to other courses. So you will definitely see inverse functions showing up later on. And the idea with an inverse function is it's something like, addition and subtraction, right? They undo each other, or multiplication and division, they undo each other. And there's a more general sort of framework for functions. How do you undo a function? But before I talk too much about this in terms of our slides and objectives and examples, let me show you the picture graphically, because we'll have to be able to sort of deal with inverses in multiple ways. So either with a table, or with the graph, or with an equation of the function. So there's lots of different ways to have to sort of deal with that. And let me go ahead and start off by looking at what it means graphically, okay? So what you're seeing up here on the board is what we used last time, and I'm pretty happy to say that a lot of students have emailed me and have been using Desmos to help them sort of complete the homework exercises. Remember, you won't have it on the exam, but it's also a really good resource. And again, it's Desmos, DESMOS.com, and it's 100% free. So what you're seeing here is just the graph in the XY plane from -10 to 10, and then in the X direction also from -10 to 10. And in Desmos, you can type in functions. For example, f of x is equal to, let's say, our good friend, the absolute value of x now. And remember, we should be pretty, yeah, that's awesome, Dalton. That's a good point. There is an app. So if you have an iPad or a phone or something like that, it's a pretty good resource to just have like right in your pocket, easy to use. It's easy to use for computations as well. So that's pretty nice. And I think the app is also free as well. Okay, but here we have the absolute value function, and it's this nice sort of V-shaped function, and we've been talking about translating it. So for example, if we were to add 1 to the x here, that would translate us over to the left by 1. And then we could say, for example, I don't know, let's add 3, and adding 3 to the outside of the function then moves us up by 3 units. And so we've been talking about, doing these sort of transformations. And then we also talked about, what happens when you compute f of negative x, or the negative of f of x. And for example, here, we could compute the negative of f of x here, just replacing every x with a negative, and it reflects it around the y-axis. And what we're going to be interested in doing, so notice that this is a function. It passes the vertical line test, right? So it hits every vertical line in at most one spot, so it's definitely a function. And here's the equation for it. So if we wanted to figure out the y value, we just have to plug in. For example, here, if we plug in 0, we get 0 plus 1, the absolute value of that is just 1, 1 plus 3 is 4. So every point you're seeing in the purple line here, or purple graph, is just obtained from that function. And what we would like to do with an inverse function is see if we can go the other way around, right? So an inverse means we're going to sort of invert the process and run it in reverse. And so what we'd like to do is take the output of the function f and treat it like the input of a new function. And we can't always do that, right? So some functions are not going to allow us to do that, but what we really are effectively doing are swapping the x and the y values. So we're switching the role of x and y from being the input to being the output. And you can do that pretty easily in Desmos just by saying something like y equals f of x. So this is the same graph, you can see it in blue, but now what I'm going to do is just everywhere I see an x, I'm going to replace it with y, and everywhere I have a y, I'm going to replace it with an x. And so what we get is this line in blue over here. And all I did was, in this equation, swap the roles of x and y. So what's really happening here graphically, it's best to see maybe this line here. And I'm going to put it as a dotted line because it's not part of any of these functions. It's just there to help you visualize what's going on. Now, what's happening with these points is, for example, if we look at this point down here at the bottom, it's at -1, 3. It's being reflected along this green line to this point down here. And really what the reflection does is it just swaps the x and the y value, okay? So when we do that, we're going to get to the point 3, -1. Okay, and we can pick a point way up here, for example. This is the point -10, 12, and we can then swap the value -10, sorry, it's -10, 12, let me put it here. So -10, 12 is this point up here. And then if we swap the x and the y values, we get 12 and -10. Okay, and that's now a point on this blue line. And so the points on the blue curve over here, you'll see now are just obtained by taking the purple curve and replacing the x values with all the y values. Okay, so that's what was done with this equation up here. Let me erase this one and this one, and I'm going to turn this off because that's the line that we're reflecting across. And if we were to change the function, the reflection would change as well, right? So we could move this over even more. Let's say we put, +4, and then this graph changes as well, okay? And one thing that you should notice immediately is that the purple graph there is no longer a function, unfortunately, right? So for example, right here, this vertical line at 10, right, intersects the graph in two spots, at -11, and then also up here, it looks like at 3. And so this doesn't pass the vertical line test, okay? Now, it turns out that there's a pretty easy way to determine when the reflection will pass the vertical line test, and it's called the horizontal line test. So if the graph, the original one, the one here in purple, passes the horizontal line test, meaning that it intersects every horizontal line in at most one spot, then the inverse will pass the vertical line test, right? So when we reflect along this line y equals x, it'll pass the vertical line test. And we can see here it doesn't, right? At y equals 10, this graph does not pass the horizontal line test, okay? And that's being reflected over here into something that this vertical line is not a function. So my first point here is just that if you arbitrarily do this, you may not get something that's a function, right? So you can't just switch the inputs and the outputs. And so we'll have to ask the question, when does an inverse actually exist? Well, it exists precisely when we pass that horizontal line test. So let me give you now a function that passes the horizontal line test. Let's say something like x cubed, and then just for fun, let's move it up by 1. Okay. Okay. Sorry, guys. I think my headset might have just went out. Let me see if. Can you guys hear me on the in the chat there? Okay. I suppose it's working. Does it? That might be better. Okay. Hopefully this is a little bit better. Sorry, guys. I had some audio issues on this side. But anyway, we were just looking at this function y equals. Okay. Yeah, I'm having to use not my microphone anymore. I think my microphone just went out. So it's coming in through a different feed, but hopefully it's understandable. Please stop me if it gets to be a little bit strange, okay? And I'll try and maybe switch out the microphone. Okay, so we've got this function f of x is equal to x cubed plus 1. And here, what I was saying is it's just this x cubed function moved up by 1. And what we would like to do is reflect it across this line. Okay, so for example, if we zoom in a little bit, we can maybe get a better look at some of the points. This point right here at 0, 1 is going to go over to this point over here at 1, 0. Okay, so this is the point 0, 1, and so we'll get a new point, which is 1, 0 on the new graph. And we should do that with every single point. And when we do, we get this function here in blue. And it's a function now because the one in purple passed the horizontal line test. So now the one in blue now passes the vertical line test. Okay, but we have to be a little bit careful with some of these. If it doesn't pass the horizontal line test, for example, like x to the 4th, then when we do this reflection, the new graph is not going to pass the vertical line test. So you'll notice now this blue line no longer does. So again, we need to be a bit careful here. So let's jump back to the slides and talk about the details of today's lesson. Okay. So what are we after today? Well, today what we'd like to do first is give the definition of inverse. So I'm going to be a lot more precise. I'm not just going to do things graphically like we're seeing here. And then we will verify that two functions are inverses. Once we do that, just like any function, we should talk about the domain and range. So we'll talk about the domain and range of the inverse and the fact that when something's one-to-one, that's when we'll have an inverse. Okay, so that's what this second objective is talking about. And then finally, the most important, yeah, sorry guys. Let's see if is that a little bit better? Maybe I can hold the phone up a little bit closer. Okay, cool. I'll try to hold it up closer so that the audio is a little better. Sorry for the issues, guys. Yeah, sorry, Isaiah. Should be a little bit better now. Okay, so the third and most important part here is to find and evaluate the inverse of a function. So what's going on there is that if we want to be given a formula for f of x, we'd also like to have a formula for the inverse. And that's what's going on in 3. And we'll do a few examples of that because for the most part, Affinity is all about that objective, right? So the homework is really going to ask you to do that pretty often. And then finally, sort of what we were doing just now is if you have something that's one-to-one, well, you should be able to graph the inverse function on the same axis. And it's exactly what I was just doing, right? You take the points, you switch the x and the y value roles, and then you just sort of fill in the graph. We'll do one more example at the end to help out with that. And I think we're sort of running a little bit behind, so I'm going to go past these objectives pretty quickly. If you need to, you can check them out in the book or watch the video. Okay, so here's the picture that you should have in mind of a function, right? So in this picture, we had an input, which we were calling x. It went into this black box, which was the function. It went through some process, multiply, division, you know, all sorts of interesting things we've seen so far. And then out of this comes the output, which we were calling y, okay? So that's the picture that we have in mind. And what we've been talking about graphically is what happens if we take the input and treat it like it's the output. So what does that mean? That means we have a picture like this. Is it possible to instead treat the output y like an input, reverse this process, and come out with the output x? And what we've already seen is that graphically, the answer is sometimes. It's not always going to be possible, right? It's only going to be possible for those functions whose graph passes that horizontal line test. And furthermore, we would like to get sort of a formula that tells us if I have this particular output, what is the input that gave me that particular output? Okay, so a little more formally, we have this definition, okay? So this is sort of what we've been saying graphically and then pictorially. The inverse of a given function f of x. So somebody gives you a function. The inverse is a brand new function, right? It's not the function f, it's something entirely new, where the input of the original function f of x now becomes the output of the new inverse function. And again, not every function has an inverse, right? It's not possible to swap the roles all the time. Yeah, Brian, so the idea there is that it must pass that horizontal line test in order for the reflection to then pass the vertical line test. So really for the inverse to exist, we need to have a function which is passing the horizontal line test, or another way to say that is that it's one-to-one. Okay, so now what I'm going to show you is the notation that we use. So it's a new function, and because it's a new function, we have new notation for it. So when this inverse actually exists, we call it f with a -1 like an exponent. And be careful, f to the -1 of x does not mean 1 over f of x, right? It's not like your regular old exponents here. It's denoting an entirely new function, which is reversing the input and the output of the function f of x. Okay. So the first objective was like, how do we determine if one function is an inverse of another? okay? And it has to do basically with the picture that we saw over here, okay? So how are we going to determine that this function really is undoing this function? Well, the way that you do that is you start with an input x in the domain of f, you throw it into this function, you run through the process, you get an output y, and then what you do is you take that output and you run it through this second machine, right? The one that you think might be the inverse, and you run it through that process there, and if it really is the inverse, what you should get back is x, because this one's just undoing this one over here. And you can also do it in a different order. So here I started with x. You could also start with a y, this y down here. So if I start with this y, run it backwards to get to an x value, I can throw that x value into this machine. It then runs it in forward, and you get back to y. Okay? So these two machines are undoing one another. And you'll notice what we're really doing there is composition. We're feeding the output of one function into the input of another. So we're forming the composition of the two functions, and that will be our method for determining if two functions are inverses, right? So somebody gives you two different functions, say f of x and g of x, both in formula form, so no graph or anything like this, and they ask you, are they inverses of each other? Well, the way that you determine is you plug one of them into the other, so you compute f of g of x, and you determine to see, do you get back x, right? I plug in the x into g, and then plug the output into f, so I get back x. If the answer is yes, then g indeed is the inverse of f. Now, there's also a second way you could have done it. Like we were saying before, you could have started basically with the y. They're using an x here, but you could have started with the y. And that's if you plug into f first, and then take the output of that and plug it into g, and it does nothing, right? So the input x gives you the same output here. And again, if either one of these equations are true, we say that g is the inverse of f, or f is the inverse of g. And you only have to check one. Now, if both of these statements are false, right? If you compute g of f of x and f of g of x, and you see that they're not equal to x, then they are not inverses. Okay? So the question here is, are they inverses or not? You compute that equation and you see if you get back x. And really, in your mind, what you should be imagining is you're asking, do they undo each other, right? Does one function undo the other one? Same way that addition undoes subtraction and multiplication undoes division. Okay, so let's actually do an example. So here are two functions. F of x is equal to x cubed minus 4, and g of x is equal to x cubed, I'm sorry, the third root of x plus 4. And we want to know, is g the inverse of that? So we can approach this problem in two different ways. We could compute f of g of x, or we could have tried to compute g of f of x. And we want to ask ourselves, is this equal to x? Because if it is equal to x, then they're inverses of each other and they undo one another. And if not, then they're not inverses, right? And that answers the question for us. So I'm just going to focus on this one. And again, you could do either one, okay? So I'm just going to focus on this one. And here, the formula for g of x is cube root of x plus 4. So this is going to be equal to f of the cube root of x plus 4. All I'm doing is replacing g of x with what it's equal to, the cube root of x plus 4. Okay, now we can use that formula for f of x. F of x takes the input and cubes it and then subtracts 4. So here's our new input. So it takes that input and it cubes it and then subtracts 4. Right? And all I'm doing is everywhere in this formula for f of x, replacing that x with the cube root of x plus 4. Okay. Now you simplify. So here the cube root of to the power of 3, those cancel each other out. And so that gives you x plus 4 minus 4. And then nicely here, the 4 and the minus 4 cancel out. So we get x. So in this case, g of x is the inverse of f of x. Okay? And we would write that in this way. G equals f inverse. And again, remember, f inverse does not mean 1 over f in the context of function. Okay, and we could have done this one as well, right? So you're welcome to try and go through that computation and see that it does indeed give you the same value of x. So that's our first objective. right? Determining if two given functions are inverses, you compute the composition and see if it gives back x. Okay. Now, graphically, what it means is that these two functions are going to be reflections of one another along that line y equals x, okay? Because all you're doing is flipping the x and y values. Okay, so remember at the start of class we said, you know, maybe inverses don't necessarily always exist. And we talked about it in a little bit of detail, but again, Destiny, how do we know it's the inverse? Let me just go back one more time to the how-to, and I'll show you the how-to. Okay, give me a second. We're having some technology issues today. Looks like some of you are getting reconnected as well. Is everybody on board? Can you hear? Give me a thumbs up if you can hear me and you can see the slide again, just before we get too far out of whack if people aren't hearing. Okay, so we've got a good thumbs up there. And so the question again was, why is this really the inverse? Like, how did we conclude that it's the inverse? And it's from this how-to, right? Again, the how-to just says you compute f of g of x and you see if it's equal to x. Here, we computed f of g of x and we saw that it was equal to x. So that's why I put a check mark here and then bam, it's the inverse. And we could have done it this way too, right? Either way. So whatever one looks like it might be easier for you, you can work. Okay, and that's that first objective. Now we're talking about when does the inverse exist? We saw with that absolute value, it failed the horizontal line test. Therefore, it was not one-to-one and it didn't have an inverse. So the statement is this: a one-to-one function will always have an inverse. Okay, so if it passes the horizontal line test, it will have an inverse. But we have to be careful. Not everything passes the horizontal line test. And some pretty important functions don't, like y equals x squared, right? I mean, that's we've seen that a bunch of times. It doesn't pass the horizontal line test. So you should be careful. And then down here is just a how-to. We've already talked about this a couple of times, so I'm just going to remind you, and then we won't do an example. The horizontal line test is the way to determine if you have an inverse, right? You inspect the graph, and you check to see if any horizontal line intersects the curve in more than one spot. If there is such a horizontal line that intersects in more than one spot, you conclude that it is not one-to-one, and there is no inverse. On the other hand, if every horizontal line intersects the graph in at most one spot, then you can say that it is one-to-one and there will be an inverse. Okay, so we know when the inverse will exist, it has to be one-to-one. And now what we would like to do is go through and talk about the domain and range of the inverse, right? Because we haven't said exactly what the domain is or what the range is. And then also, if you give me a formula for a function, can I then determine a formula for the inverse itself, right? And it turns out that for a lot of functions, you can. Okay, so let's attack this question of domain and range, okay? So here is the picture that we had in mind for a function that was just sort of thinking about it as the domain and range, right? So the domain is the set of inputs to the function. So here A is an input, and the function is applying the input here, and it's getting this output of B. So we would write that typically as f of A is equal to B. And B is an output, so it would be in the range of f. The set of all outputs is called the range. The set of all inputs is called the domain. And it's pretty interesting what happens here for the inverse function, because what the inverse function does is it just switches the input and the output. So it takes B as the input now and outputs A. So we would write f inverse of B is equal to A here. And what that means is that the domain of f inverse is really the range of f. And the range of f inverse was the domain of f. So when you take the inverse of the function, the domain and range swap. And that's what's being said here, okay? So the range of a function f of x is the domain of the inverse. and the domain of a function ends up being the range. And that's just because you're swapping the x and the y values. I think it makes sense. Okay, and you have to be careful with some of these. I'll show you an example later on where this restriction really is necessary. We have to be careful about what the range and domain is. Okay. So here's, I think, the most important topic for the class today, and it's really the types of questions you'll see on infinity. Okay. So the types of questions you're going to see on infinity here are going to be asking you to, given a formula, compute the inverse of the formula, right? So the inverse function here. And algebraically, it's going to make sense in terms of what we did graphically. So somebody's going to give you a formula for f of x, okay? And you're going to want to find the inverse. So the first thing that you should do is really make sure that it's one-to-one, because if it's not one-to-one, you're doomed to fail immediately, right? There is no inverse if you're not one-to-one, and so you won't be able to find a formula for it. So you need to make sure that the problem's telling you that it's one-to-one or that you believe that it's one-to-one. And the next two steps are different from what you'll find in the textbook. The textbook swaps step 2 and 3, but I'm gonna do it this order because this is how I sort of think about it. The first thing that I do is interchange in the formula x and y. So everywhere you see an x, you swap it with a y, and everywhere you see a y, you swap it with an x. And what that has the effect of doing is producing the inverse, right? Because we just switch the input with the output. And then if it is a function, you should be able to solve for y and get the output of the function in terms of x. So then you'll try and solve for that y, and that formula that you get for y is the formula for f inverse. Okay, but the algebra can get tough. Okay, so let's do a couple of examples here and sort of see what happens with the algebra. Because the last step there, solving for y, is not always the easiest thing. But again, I'll just remind you that the book says solve for, I think, x first, and then swap x and y. So that's the order they say. And it doesn't matter what order you do it, as long as you're swapping and then solving for the appropriate output. Okay, so let's see some examples. Okay, so the first example, we're going to take a rational function. Remember, a rational function is just a ratio of two polynomials, and we're going to try and compute the inverse. So let's find the inverse of f of x is equal to, let's see, what did I say? 3x over x minus 2. Okay. And, you know, if you weren't sure about the one-to-one, probably the best way to do it, the only tool we have is the horizontal line test. So you would graph this somewhere like Desmos and then recognize, oh, okay, this thing passes the horizontal line test. So maybe we should do that just so we can see it there on Desmos first, and what the graph actually looks like. So we said 3x over x minus 2. Okay. And what you're seeing here is that line in purple, and if we were to zoom out, you'd see a little bit more. It's actually one of these like 1 over x functions. So here's the function, right? It has a vertical asymptote right there at x is equal to 2, because 2 is not in the domain of this function. But what we'd like to do is reflect it across the line y equals x. And we'd like to do it not graphically, but with the equation, okay? So let's come back and do that here. So your first step is to remember that f of x is really y. This is the y value. So this equation is the same thing as y equals 3x over x minus 2. And then from here, you'll want to try and switch the x and the y, right? So that's the next step. And that's to get an equation for the inverse. So flipping the x and the y gives x is equal to 3y over y minus 2. Okay, so that's that first step, swap the x and the y. And again, that's equivalent to rotating across that line, x equals y. And from there, we need to solve for y. So we need to sort of get that y out of the denominator. Okay, so what should I do to get that y minus 2 out of the denominator there? What can I do to both sides of the equation? Well, we don't want to quite multiply just by y. It has to be a little more than just y, because if you multiply it by just y, it wouldn't get rid of this y minus 2. Yeah, so we need the y minus 2 on both sides. So we multiply both sides by y minus 2. This side gives x times y minus 2. And this side, the y minus 2 cancels out. And you're left with just 3y. Okay, so the advantage of this is that there are no more fractions. Now we can work on isolating the y on its own. To isolate the y, don't add 2, right? Be careful here. We need to distribute this x first. So this is really x times y minus 2x is equal to 3y. Okay, so we need all of the y's on one side of the equation. So I'll put this 3y to the other side. And I'll move everything without a y to the other side. So that 2x is going to come to the other side. I'm going to put it up here. So here we get xy minus 3y is equal to 2x. So I subtracted the 3y from both sides and added 2x. Okay, so what should I do next? How am I going to isolate that y on its own? What's my next step here? Well, we can't quite divide by x, because if we divided by x, we'd have a 3y over x on this term. There's no x here. So we don't want to quite divide by x. How will we get y on its own? Well, we don't want to divide by y minus 2 either. There's something we have to do to this side before we divide. Okay? So what should we do here? What do you notice in both of these terms? So there's a y in both terms, okay? And what that means is that we can factor the y out, okay? We want to get y on its own. So here we have two y's there, but if we factor the y out, we get y times x minus 3 is equal to 2x. And now there's just one y, right? There's not two y's over here like we had before. And what we did was we factored out the greatest common factor, which was that y, okay? Okay, so now what should we divide by? It's not x, it's not y, but how are we going to get that y on its own? What should we divide by? Okay, yeah, that x minus 3 now is the last term, and so we get y is equal to 2x over x minus 3. And then the last step is to realize, okay, this is the inverse, so now we would write it like this. F inverse of x is actually 2x over x minus 3. Okay, so let's come back to Desmos really quick and see what that looks like graphically. So remember, here was our function in purple, and we wanted to get an equation for this thing in blue, right? So that's what happens when we swapped the two of them. So we want something that's like this blue one here. So how do we do it? Well, we have that equation that we just came up with. It was y equals 2x divided by x minus 3. And there you have it. It's exactly the same as this graph right here. Okay, so what we have is an equation where the x and the y values are swapped out. And that's what we wanted graphically, and that's what we did algebraically. Okay, so let's just do another example of this because again, the hard part here was the algebra. And like I said, this is the main part of the infinity homework here are these sorts of expressions. So let me do a second example. In this case, we're going to do 1 over 7x minus 1. Okay. And really, if this question, if you weren't sure it was 1-to-1, you should check. You should graph this thing and check to see that it's 1-to-1, because otherwise you won't be able to actually solve the equation. You'll just get stuck somewhere, or you'll get plus or minus or something like that in the equation. You won't be able to uniquely solve for the y value. In those cases, what you would say is that no such inverse exists, right? Similar to when you're dividing by 0 or something like this. Okay, so let's go through this. We've got y is equal to 1 over 7x minus 1. And we're going to swap the role of x and y. Okay, so here this becomes x equals 1 over 7y minus 1. And what we just did was reflect practically over that line y equals x. Okay, we swapped out the x and the y value. And now we need to solve for the y. What should we multiply both sides by? Yeah, we need to clear out that denominator. So 7y minus 1. Here we get x times 7y minus 1. And on the right-hand side, the 7y minus 1 and the 7y minus 1 we multiply, cancel each other out, and you're left with just 1. Okay? So really, we're multiplying both sides of this equation by 7y minus 1. So over here, we're going to have to do the same thing we did before. What do we get for this expression here on the next line? What should it look like? Yeah, so we're distributing the x, so it should be 7xy minus x is equal to 1. And the reason why is that this doesn't isolate y on its own. There's this minus 1 here, right? So we need to distribute the x through so that we can get just this one single term with y on its own. Now we'll have to add the x to the other side. And then our last step is to divide by what? We want to isolate y on its own. What do we need to divide by? Yeah, we need to clear out the 7. So we've got to divide by a 7. And then we have to clear out the x, right? So that the y is left on its own. So we'll divide both sides by 7x. So we get 1 plus x over 7x. And then we finish off the problem by saying that's the formula for the inverse. You asked me to compute the inverse, and there's the formula, right? So I'll box my answer. Remember, don't forget to include your supporting work in your notes, and on an exam, you really need to show supporting work. Otherwise, you probably wouldn't get much of any credit for this problem. Some students can see the inverse here, like you can see that, oh, like undoing the -1 is adding 1, and then undoing the multiplying by 7 is sort of dividing by 7. So some people can sort of see those things, but I would, that it's better to just show your supporting work, okay? So there's another example. And I suppose we should see this graphically as well, just so we can verify that what we've just done is correct. And this is a good way to check your work on the homework and see that you've done sort of the right thing. So here, we no longer have this 3x function, but instead 1 over 7x minus 1. So 1 divided by 7x minus 1. And it's this graph here in purple, and we need to zoom in to get a better sense of what it really looks like. So here it is in purple. And we're going to be interested in finding a formula for the inverse, like we did. And it's going to be this function here in blue, because that's what's the reflection across that line y equals x, okay? And the formula that we got was y equals 1 plus x, and then that whole thing divided by 7x. And there it is, okay? So we've now obtained a formula for that graph reflected along that line y equals x. And again, we're reflecting along this dotted line right here. So there's our inverse function. Okay, and you'll notice 0 is not in the domain, right? So that means 0 is not in the range of this function up here. Something that maybe you didn't see before. Okay, one last example of this process, just to show you that there are issues with domains. Okay? We have to be really, really careful when we do this process because we may get a formula which has a bigger domain than the actual inverse. So let's see an example of that. I'm thinking of something like the square root function, the square root of negative 6x minus 1. Okay. And before we do anything with this function, let's go ahead and, like, before we find the inverse, let's think about the domain, because there's some issues here with the domain. And I'm going to say the domain of f of x, because we need to be clear about what function we're talking about. And here we're talking about the domain of the function f. So in the chat, tell me what inequality you would solve if you wanted to determine the domain of this function. This is a good review. Remember, the problem here is this square root. So what inequality should we look at? Well, I'm not even really looking for the answer here, Jordan. Just what inequality would you look? And we'll go through the steps of solving it, right? So remember, we don't want to take the square root of anything that's negative, right? So what inequality should we set up here to find the domain? Well, I suppose just as a quick hint here, it has something to do with negative 6x minus 1. So we want that thing to be non-negative. So what inequality should we put here? What are we going to say about negative 6x minus 1? It's greater than or equal to 0. That's exactly right. Okay. We need to make sure that anything that's underneath the radical is greater than or equal to 0. Okay, so let's go through and solve this. We move the 1 to the other side, and then we divide by the negative 6. And remember, when you divide by a negative, the radical flips around. So here, the domain is actually the numbers from negative infinity all the way up to negative 1/6, including 1/6. Okay, and let me bring up the graph so you can see it, just so we're all clear about that domain. Okay, so here we're looking at the square root of negative 6x minus 1. Oh, I need the graph. Okay, so there you can see it's going to the left there, so its domain is all those values to the left of whatever this number is, and this number right here is that value of 1/6, 1.67, 66666, but here they round it to 7. Okay, so there's our graph, and you'll notice the range. What's the range? Just pictorially, somebody tell me what the range is. What do you see there in the range? And it keeps going up, right? It keeps getting larger and larger as we go to the left. What's the smallest y value and the largest y value? 0 to infinity. Okay. So we're going all the way from 0 to infinity, and we include 0. So we shouldn't have a parenthesis there, we should have a bracket. Okay, so here the range of this function f is this. And what this means is that the domain of f inverse is going to be from 0 to infinity. Because remember, when you compute the domain of the inverse, it's actually the range of the original function. But that's not going to be apparent from the equation. Okay, so let's just go back and now sort of not talk about domains here, but just this equation. So what we would say is y is equal to the square root of negative 6x minus 1. That was our first step. we swap the x and the y, so we get x is equal to the square root of negative 6y minus 1, and then we solve for y. Okay, so if I want to start isolating the y on its own, how do I get rid of this square root? What do I need to do both sides? Okay, you need to square it. So this is x squared is equal to negative 6y minus 1. I think Jordan might have had some problems, but we've only got 4 more minutes, so those of you having issues, I'll ask to just watch the rest of the video. Okay, so now we want to get the y on its own, so we'll add 1, and then we'll divide by the negative 6. Okay, so then the formula for the inverse is x squared plus 1 over negative 6. So this is what we should find for the inverse. However, you'll notice that if we just look at this, it looks like the domain should be any real number, but it's not. The domain is really the range of this function, and we can see that in this case if we look at the graph, okay? So here was that function we were looking at, the negative 6x minus 1. And if we then look at our new formula, which is y equals x squared plus 1, and then all of that divided by 6, or I'm sorry, negative 6, you get this curve here. And you'll notice that this part over here is not part of the inverse. Really, the inverse is from 0 out to infinity. It's this piece over here. So even though we can do this process just with the formula, we should be really careful about what the domains really are, right? Otherwise, we'll run into some issues here. This part's not reflected along this part of the graph, okay? Okay, so that was that formula. And then the last thing that I wanted to point out was that you should be able to do some of this sort of stuff graphically. So let's talk a little bit about that. We've already sort of seen plenty of examples. But here's a graph of a function that passes the horizontal line test, so it has an inverse. And what we would like to do is sketch the graph of the inverse without any formula, right? So we're not doing what we had before, but just given the graph. And it's pretty easy. What you do is you just pick points on the graph. For example, this is the point 2, 4. And then you reflect that point along the line y equals x. So that means just replace x with y. So this point 2, 4 will get to the point 4, 2, which will be somewhere over here. This point here at 1, 1, if I switch the x and the y values, just stays at the same point. The point 0, 0 stays there. This point here has a y value of 2, and so it'll get reflected to a point over here. And so the graph should look something like that, okay? Now, here it is a little more precisely. You pick this point up here and you reflect it over there. You pick this point here and you reflect it over here. This point stays the same because the x and the y values are the same. This point stays the same. And then you just sketch in the reflected points. Okay? And you should be able to use these formulas to compute something like f inverse of 3. For example, if this is the function f of x, and you want to compute f inverse of 3, instead of going to like the x-axis at 3, you go to the y value and treat that like the new input. Bam, and then you come back down to the x-axis over here. So you would say something like f inverse of 3 is equal to, like 1.7. Okay, so just one last example here of this process. So here's a function, passes the horizontal and the vertical line test, so an inverse does exist, and we'd like to graph the inverse. So again, what you'll do is just pick points on this curve, ones that you can see the x and the y values pretty easily. For example, this point here is the point 4, 2. And so if I swap the x and the y value, right, it goes from being the point 4, 2 to the point 2, 4. So it's going to go up to this point up here. Okay, so that point goes up there. Let's pick another point here. This is the point x equals 2, y is equal to 1. And if I swap those x and y values out, I get to this point over here, right? And then here, this is the point x equals 1, y equals 0. And so when I swap those out, I get x equals 0, y equals 1. Again, all I'm doing is swapping out the x values. And you can see sort of the curve here just looks like this. It matches this one and comes up along that way. So you just plot as many points as you need until you get the general shape of the graph. And because it's a sketch, it doesn't necessarily have to be perfect. And again, what you're really looking for is that it's the reflection along that line, y equals x. So that's what we're seeing in this graph here. And I see that it's 11:51. Here's just a quick reminder of those inverse functions. I'll be around for the next 5 minutes or so if you have a question or two. And so let me know. But thanks for being here, and thanks for watching if you're watching.